Hello everyone. Sorry I'm not here in the meeting today. What I'm going to do instead is in this video show some of the work we did this summer. I'm going to highlight combustion of PMMA, but if you send me a few pieces of data, we can include any material of interest in our database. So using PMMA, I'm going to show how simply we can find the heating value, adiabatic flame temperature, equilibrium composition, and equilibrium flame temperature. So I have already logged into test at thermofluids.net. You can create an account in seconds, and if you let me know, I'll make your account permanent and you can access the apps I'm going to show you. So if you recall, we already had this lot of tools for calculations based on Java-based applets. Now that the browsers are not supporting Java, this summer we have been converting them into what is known as client-server HTML5 based apps. So to get started, we follow the system analysis. It can do a lot more than combustion, open branch, specific branch, and come to combustion and chemical equilibrium node. There, these are the equilibrium apps, and these four are premix, non-premix, but these are simpler, complete combustion kind of apps. So we'll just find adiabatic flame temperature based on complete combustion first. So we go for an ideal gas mixture model and click on the HTML5 page to launch the calculator. Very briefly, it has a few panels: the composition panel, where you compose the reaction; state panel, where you find the states of fuel and oxidizer and products. Graphics panel shows where the states are. And in the IO panel, you can write short coding almost. So I'll show you. For instance, suppose we are trying to find the heating value of PMMA. So in the composition panel, all we do is go select PMMA. So we go down. I think I put it here. Yes, say we have solid PMMA. So I just selected 1 kilomole of PMMA. I click add button. So the fuel is composed. Of course, it's pure fuel. And to find the heating value, we construct a theoretical reaction, theoretical combustion with air. So theoretical means all carbon goes to carbon dioxide, H goes to H2O, and there is no excess air, oxygen left or fuel left. So after selecting, of course, we have to click the execute button here, and then the reaction will be balanced here. Here is PMMA, and we'll see the balanced reaction. So this is a standard reaction, so you can see the balanced reaction is shown here. And of course, if you go oxidizer or fuel or products, you can see the product composition, a result of complete combustion. So it's really a trivial problem. So in the state panel, what is heating value? Heating value is if the products and reactants, they are all flowing at room temperature and pressure, 100 kPa, 100 standard temperature and pressure. Notice that state 1 is linked with reactants and state 2 is linked with products for premixed conditions. So pressure doesn't change and temperature doesn't change. Well, so we found, also you'll see the partial properties of every component is shown here. So now that we have found state 1 and state 2, we go to the IO panel, and we know that the heat transfer Q dot, we must be cooling. So let's say Q dot out must be equals M dot 1 star H1 minus M dot 2 star H2. Of course, M dot being the mass flow rate must be equal M dot 1 and M dot. So when I write this equation, Q dot out is calculated, a very large number, but that's for 1 kilomole of fuel. So if I divide Q dot out by, so that will be the it'll be the lower heating value. Lower heating value would be Q dot out divided by M dot 1 per kg of the mixture flowing in. Well, this is not the heating value exactly, because it is per kg of the mixture, so we better find out how much fuel is flowing in. That would be the lower heating value. So this is the heat released, and we had 1 kilomole of fuel flowing in, and so really the equation should be Q dot out divided by the fuel mass, which is, in this case, for the composition panel, the fuel mass is 1 kilomole we added, so the mass is 100 kg for PMMA. So really it is this. So 25.979 will be, so this is in kilojoules. This is in kilojoules per kg. Of course, 25.9 will be our million joule per kg, will be the enthalpy of combustion for PMMA, solid PMMA. Okay, if we wanted to really find the adiabatic flame temperature, in that case what we should have done is, let me get rid of this. Let's clear this, let's clear this area, and in that case the enthalpy, there will be no heat transfer, therefore the enthalpy of the products, H product, let's call it HPR, must be equals m dot 1 times H1 divided by m dot 2. Of course, H2 equals H1 in this case, is as simple as that. So we could just go to the state panel, and in state 2 we'll say we don't know the temperature this time. Instead, H2 equals H1, and that will calculate the adiabatic flame temperature, which is 2438 Kelvin. And of course that's for complete combustion. So let's write down this number 2438, and we'll compare that with equilibrium flame temperature. So to get the equilibrium composition or equilibrium flame temperature, again we go to the combustion node and we launch one of those chemical equilibrium analysis tools. Come to HTML5 page and essentially do the same thing over again. PMMA we choose, this looks almost identical, and we are doing this time, notice that there's no theoretical reaction anymore, it's equilibrium combustion with known excess or deficient air. By default it's at 100%, that means there means no excess air or no deficient air. You could put a percent there, suppose there is excess air or excess fuel. So as soon as we click the execute button, oxidizer is fixed. We have decided how much oxygen, nitrogen are flowing in, but the products are unknown. So we can go and select what all we want in the products from this list, or typical combustion products, you can just click this button and it kind of selects those, and we can click the add button. We don't know their amounts, but we have chosen these products to be present, these components to be present in the products. We go to the state panel. As before, the inlet state is 100 kPa and let's say 298 Kelvin. But the exit state, we really don't know the temperature. Let's just guess something. Suppose we say it's 2500 Kelvin. Then it takes a little time to compose the mixture. Notice that the mixture is way complicated. You can go to the composition panel at a given temperature. The product's compositions are found and the reaction is balanced. The equilibrium reaction for the given temperature is what it finds. But is this the adiabatic temperature? Well, to find out, we can figure out how much heat is going, Q dot, heat transfer is m dot 1 times H2 minus H1, right? So this must be the heat. Oh, sorry, I forgot the star here. Calculate. So heat transfer is a very large positive amount, which means Q dot is positive, means we are heating the combustion chamber to get this 2500 Kelvin. So obviously the adiabatic flame temperature must be less than that. Suppose we say, okay, maybe it's 2000 Kelvin. And then recalculate the products, go to the IO panel and calculate, click the calculate button here again. And this time we got a very large negative number. So obviously we bracketed the temperature. And if you just do a little trial and error like this, we can show that the temperature will turn out to be about, I believe, 2290 or something like that, very close to that. Or calculate, and when you go to the IO panel, now this number is way smaller. Of course, you can tune it to even smaller number. So anyway, so this is a tool, a handy tool for any thermodynamic calculation. Pretty soon we'll relax the, notice that only temperature is the input here. We'll make enthalpy as an input too, so that you could directly say H2 equals H1 and find the adiabatic flame temperature and composition. Equilibrium flame temperature and equilibrium composition. Anyways, so if you want, right now at this moment we only have for our research community, I only have cellulose and PMMA here, but I can add any other fuel here. Only thing you have to provide me is the formation enthalpy and approximate CP value when it's vapor, which is not a must, and the entropy value, the standard entropy. That's it. Thank you. I'll not make it any longer.